Hello everyone. Today we're starting a new series on methods on asymmetric encryption, and we're starting with the discrete logarithm. So to understand what we're talking about is we are not dealing with infinite numbers. So we are dealing with a finite body of numbers, which means that there is a cutoff point in which numbers return. An example of this, which we've covered in another video, is the Galois field, which is cut off by an exponential, in this case p to the power of n. An example of the application of the Galois field is AES, the Advanced Encryption Standard, Rindell, which operates on a Galois field of 2 to the power of 8. Another property these functions have, which we use for asymmetric encryption, is that they have a one-way property with a trapdoor. So unlike hash functions, they're not inherently one way and there is no way to return to the original. There is a way to return to the original if, for example, a certain password or key is known. So going to the discrete logarithm is the inverse of an exponential. So if we have this equation here, y equals g to the power of a mod p, this is obviously very easy to calculate if you know all the variables. However, the inverse, which is a as the logarithm of y, logarithm to the base g of y mod p, is very hard to calculate. In fact, it is basically impossible to calculate. The only way to do this is by guessing or trying until you find a solution, and this is what we'll see a bit later in the video. To illustrate, I've plotted here the functions we're dealing with. So first of all, this is the function y equals 2 to the power of a. You can see here it's a typical exponential function which grows rapidly after a certain extent. So in this case, it doubles every time a gets incremented by 1. Now the inverse of this is also very easy to calculate. So the inverse is just a logarithm, in this case the dual logarithm of a, or log to the base 2 of a. So as you can see here, that's a normal logarithmic function which is continuous. Now the problem we have here now is that we are dealing with discrete values because we take the mode. So we have the same equation, 2 to the power of a, alpha in this case, mode 23. Now let's see what this looks like. You can see here it starts like a normal exponential function, however then the output is seemingly random. You can see here scattered all over the place all the different values and all the different results for different values of a on the x-axis here on the bottom. Now we are dealing with a finite body of numbers 0 to 22, which is this room of the number room of Z23. So if we, for example, wanted to find a value alpha for this equation here, 2 to the power of 10, this is very easy to calculate because we just take 2 to the power of 10, which is 1024, and if we take the mode 23, that's 12, and so we know that this is this dot right here. However, the inverse is impossible to calculate, and I will show you why. As you can see here, we have alpha, and we have now all the numbers we need basically. Alpha equals 11 to the power of 8 mode 13. Now 11 to the power of 8 is 214 million and so on. Mode 13 equals 9. Now the only thing we get is alpha, the value for alpha, which is 9. The only way really to get to the inverse, which is a, like the exponent, the only way to do this is by basically writing out all the possibilities that this function can have, and then as you can see already, this is not constant, and the only way to do it is, as I said, to try out and to basically to guess your way around this table, which could go on obviously forever. The larger our prime number is, we use for modes. So in this case, we find the value of 9 here, and we can deduct now that the value for a is 8. As you can also see, there are numbers repeating, so there is not really a singular answer to that. I hope this clarifies why the discrete logarithm is used for asymmetric encryption, since there is no way to calculate the inverse. Thanks for watching, and I see you in the next video in this series.